Okay, welcome to this panel, NASA Research Plans for Assured Autonomy for Aviation Transformation. I'm Sanjay Garg from NASA Glenn Research Center, and I have the pleasure of being the moderator for this panel. And I will tell you, this is the first time I'm talking while sitting down to an audience. I'm so used to being a technical presenter, I have to stand at the podium and talk, so I'm a little uncomfortable, but hopefully I'll get used to it. I don't have to talk too much though, thankfully. So we have a very distinguished set of panel members. Starting to my left is Mr. Rob Pierce, who is the Director for Strategy, Architecture, and Analysis from the NASA Aeronautics Research Mission Directorate. This is about the aeronautics research in NASA. So all the panel members are from the NASA Aeronautics Research Mission Directorate, and we would probably refer to it as ARMD. So you'll hear the acronym ARMD many times. So Bob Pierce, who is the Director for Strategy, Architecture, and Analysis. Dr. John Kowalowski, who is the Program Director for Aerospace Operations and Safety Program. Then we have Dr. Ed Wagner, who is the Program Director for Integrated Aviation Systems Program. We have Mr. Jay Dreyer, who is the Director for the Advanced Air Vehicles Program, and Mr. Doug Rohn, who is the Program Director for Transformative Aeronautics Concepts Program. So the objective of this panel is to share with you all the status in the planning of the autonomy research in NASA aeronautics programs. As some of you might be aware, NASA's aeronautics program has been restructured to focus on 6 strategic thrusts, and assured autonomy for aviation transformation is one of the 6 thrusts. So these thrusts are all giving the redirection of the new NASA program in fiscal year 2015, and the new programs have come in effect now starting January once the 2015 budget was passed. So I won't talk much for the rest of the slide. Go to the next one. Basically, the way we're going to achieve our objective is we're going to have brief presentations from Bob and the 4 program directors talking about how their programs are addressing the autonomy research area. And this is the time we have allocated for them based on the amount of autonomy that is expected to be in their programs. And we will have presentations by them, and then at the end we will have ample time for question and answers. So while they're presenting, you can still have 1 or 2 critical questions if you want to have, but let's keep the time for discussion at the end. So I'll start with some introduction of the panel members. So I've just given you their titles, but starting with Bob. Bob is the Director for Strategic Architecture and Analysis Office in the ARMD. He is responsible for aeronautics research, strategy development, and strategic systems, portfolio, and progress analysis. Bob is focused on the alignment of the Aeronautics Research Mission Directorate strategy, programs, partnership, and resources to achieve a global, sustainable, and transformative vision for the future of aviation. Welcome, Bob. Next, John. I have John next, and I have all these bios in my little thing, so I have to read it very carefully. So John is the Director of the Aerospace Operations and Safety Program. This performs foundational air traffic management and operational safety research to enable the development of revolutionary improvements to and modernization of the NAS, National Aerospace System, as well as the introduction of new systems for vehicles whose operation can take advantage of the next-gen system. Dr. Kowalowski has a bachelor's of science degree in mechanical engineering from MIT, Massachusetts Institute of Technology, and master's and doctor's degree in mechanical engineering from the University of California at Berkeley. Welcome, John.
Thank you, Sanjay.
Next, Dr. Ed Wagner. He is the Director of Integrated Aviation Systems Program and is responsible for the overall planning, management, and evaluation of the, let's see, this is better this way. You always learn. He's responsible for the overall planning, management, and evaluation of the Directorate's efforts to conduct integrated system-level research on promising vehicle and operational technologies in a relevant environment that meet energy, environmental, and mobility objectives. I will move to his education. He's an associate fellow of AIAA. He received a bachelor's degree in aerospace engineering from Auburn University, a master's degree in mechanical engineering from Southwest Methodist University, and master's and doctoral degrees in engineering management from George Washington University. Welcome, Ed. Mr. Jay Dreyer is the Director of Advanced Air Vehicles Program and is responsible for the overall planning, management, and evaluation of the Directorate's efforts to conduct high-quality, cutting-edge fundamental aeronautics research for a wide variety of vehicles. Mr. Dreyer served as the Senior Technical Advisor for the ARMD previously. He was responsible for the technical oversight of all ARMD programs. And he has also previously worked with Orion Systems, DARPA, and Navy. He holds a Bachelor's of Science degree in Systems Engineering from the U.S. Naval Academy, so he's a Navy guy. Don't hold that against him, the Air Force folks. And has a master's degree in ocean engineering from MIT. Thanks. Welcome, Jay. Next is Doug Rohn. And I know him a little better than the rest because he's from NASA Glenn Research Center. Worked with him in the past. He's the director of the new Transformative Aeronautics Concepts Program. And he's responsible for the overall management of the efforts to cultivate multidisciplinary, revolutionary concepts which can knock down technical barriers and enable aviation transformation. He has been part of the NASA project management team for over 35 years. He earned a bachelor's degree from Cleveland State University and a master's degree in University of Toledo, both in mechanical engineering. Welcome,
thanks,
Doug. And next we will start with Bob, who will give you an overview of the autonomy planning in the NASA aeronautics program.
Okay. Thanks, Sanjay, and thanks for spending however long this panel is, a couple hours, whatever it is.
2 hours,
2 hours.
Yeah.
Thanks for spending 2 hours with us after lunch. I have to just before I start, though, Sanjay reading the thing off the iPhone just reminded me. About a year ago, my oldest son got married, and so unexpectedly to me, as they're standing up and they wrote their own vows, and as they're about to read their vows, they both pull out their smartphones to read their vows. And that's the point at which I knew I was getting old, because I was like, are you kidding me? They pulled out their smartphones to read their vows. Anyway, we can't do anything without these things anymore.
Right.
So with that, and so speaking of that and autonomy, I guess there's some relationship there. So what I want to do is give you put autonomy in the context of our strategy as we move forward, and then talk a little bit about some of the strategic planning we've been doing with respect to getting the autonomy thrust off the ground, and then I'll describe a little bit about how the autonomy strategic thrust fits within the context of the program. So that'll be the context of my talk, and many of you have seen this by now, but just to give you a little reminder and again set the context, this is the aeronautics thrust as we go forward. On the left-hand side, you see sort of the major drivers that we're looking at as a community. On the top is global mobility, and it's really interesting to look back just over the last 10 or 20 years. In the last 20 years, if you look globally in the last 20 years, the number of unique city pairs that are being supported by the aviation system has doubled. The real cost of air transportation has fallen by half. In the developing economies of Asia and Latin America, demand for air transportation has tripled in the last 10 years. So the amount of demand growth that is upon us is tremendous, and obviously that's leading to the kind of market growth and demand for aviation products that when you read the Boeing and Airbus market reports, that's what drives all of that. So there's a tremendous pull to increase the capacity, increase the complexity, increase the amount of service we get, and that's going to drive, as I said, complexity, and it's going to drive a need for for increasing intelligence to be embedded in our systems. So that's one of the major drivers. The other part of that is, as that demand grows, it does put pressure on our environmental and energy issues, both local environmental issues as well as global, climate change issues and so forth, and energy volatility and its impact on the affordability of aviation and the ability for airlines to confidently plan for the future. Then finally, and most apropos to autonomy, is the whole area of technology convergence. We're seeing an exponential growth in IT and sensors and Internet of Things, and so many tremendous opportunities are coming. They're finding their way into aviation, first in the form of UASs and the burgeoning growth in that sector, and the desire for those vehicles to fly throughout the NAS for a whole wide variety of new aviation missions. So that push is happening rapidly, and if we don't get ahead of it, both in terms of serving the near-term needs to get that initial access to the NAS, but in the long term, providing the kinds of autonomy technologies that allow those systems to actually operate safely and efficiently in this new and complex aviation system that we're finding our way into. So that's kind of the context. You can see we have 6 thrusts. And many of them are emphasize the kinds of things we've been doing over time. So the safe, efficient growth in global operations is really about, in the next 5-10 years or so, is really supporting FAA's push to implement next gen, and we are supporting that with technology and automation platforms that can make sure that's done in an integrated and efficient way. And then as we look to the long term, looking beyond next gen, and what can, in fact, autonomy bring us that allows us to actually operate the system in a very different way and beyond perhaps what the limitations of human cognitive limits as the complexity of that and the density of the system grows. We'd like to see innovation in commercial supersonic aircraft. Again, we look globally, the doubling, again, of the number of unique city pairs that are out there. Those city pairs have very long stage lengths. We'd like to reduce the time between those city pairs, and global supersonic aircraft is certainly a promising way to do that if we can solve the major environmental issues associated with that. At the same time, really want to push on our commercial vehicles to become as efficient as possible and to transition to lower carbon propulsion means, whether that's fuels, the energy source, or the propulsion system itself. We're not going to be, if you look at the growth in aviation, as I mentioned, we can't just sort of make the system a little bit more efficient every year and expect the emissions to go down. It's the mathematics doesn't work. So we've got to innovate. We've got to find other ways to get the carbon out of the equation if we're going to continue to grow and to reduce our impact and our contribution to climate change. And finally, as I think everybody here knows, we as an aviation community have done a tremendous job at improving safety and bringing the accident rate down to a very, very low level. So what do we do as we look forward? How do we continue to improve safety? Well, we need to really start to look or continue to look system-wide, look prognostically, look proactively, try to understand what's happening, what the system states are in real time, understand where the nominal is not off-nominal, where the off-nominal issues are, and what we can do over a variety of timescales to address those off-nominal conditions and those hazard conditions that might be arising, both in terms of current operations as well as we look at the evolution of the system and the introduction of these new assets. So we're taking a major thrust at looking at how do we innovate around real-time system-wide safety assurance. And finally, what we're here to talk about today is assured autonomy for aviation transformation. Tremendous, we can't sit here today and predict all of the potential applications and benefits of enabling these increasingly autonomous systems. The ability for humans and machines to cooperate and interact and achieve goals that can't be achieved today through that mechanism. And so, we're here to enable, to address the really significant issues that have been laid out in terms of the NRC study. And in fact, my next chart is on the NRC study. So earlier this week, there was a panel on the NRC study, Autonomy Research for Civil Aviation. That's a study that the Aeronautics Research Mission Directorate sponsored, because we wanted the community's input, the community's perspective on what the future holds with respect to autonomy, the possibilities, the benefits, as well as the issues. And you can see a quote from that report that civil aviation is on the threshold of a potentially revolutionary change in aviation capabilities and operations, but there are serious unanswered questions about how to safely integrate these technology advances into a well-established, safe, and efficiently functioning NAS. That's, I think that's really the driving motivation for NASA and what we're trying to accomplish. There's plenty of demand. There's plenty of folks out there who want to operate, but we as a community, and specifically NASA as a leading research provider, need to get out in front and answer these questions. They did a series of recommendations in terms of a research agenda, and again, I'm sure they went through this in some detail earlier this week, so I'm not going to belabor it, but you can see the kinds of things that they felt were really critical to addressing those safety and efficiency functions, adaptive non-deterministic systems, operation without continuous human oversight, modeling and simulation, V&V, and so on. So we're taking those in to our more specific research planning and looking at where we've got the capability to address those, and looking where others have capability where we can partner and make sure that the full set of these agenda items are addressed at some level. So a tremendous benefit to us, and I think to the overall civil aviation community, has come from this study. Beyond that, we also have gone through an internal strategic planning activity for autonomy. We called it the Intercenter Autonomy Study Team. We put it in that little graphic to the side, shows the overall vision we have for aviation in terms of global, sustainable, and transformative. And the bubbles, those little bubbles you can't read, talk about how autonomy can help us get to those kinds of visionary activities. We went through and we looked again in a little bit more detail than obviously what the NRC could do in terms of what capabilities NASA has to bring to the table, how those relate to the requirements for autonomy that, say, the NRC and others have laid out. So it allowed us to then say, these are the kind of research themes that NASA can best take on. And John Kowalowski will talk more about where we are in translating this strategic planning into more detailed road mapping and investment planning for the Mission Directorate. So with that, just a couple of words on how the programs relate to the strategy. As Sanjay said, we've structured the programs to address the strategy, but we didn't try to say, okay, one program, one strategy, and that's it, because these strategies cut across the various disciplines, the various focus areas, and so we provided a perspective that said, we have a program that'll provide planning, leadership, but we expect the participation and cooperation of the other programs as we move forward for all of these thrusts, not just autonomy. But in the case of autonomy, airspace operations and safety, John Kowalowski's program will provide the overall leadership for planning the roadmap for the thrust, and will execute a substantial number of elements within the scope of its program. But that is sort of the center of gravity for autonomy, but providing an overall leadership function on behalf of the mission director to bring all the other programs into that research planning. The Advanced Air Vehicles programs, Jay Dreyer's program, will support that planning of the roadmap and look at those elements that fit within the context of advanced air vehicles. And that could both be, obviously, vehicle-centered autonomy issues and both the benefits that autonomy could bring to a vehicle, but also how we can potentially change how the aircraft is configured if it's a more highly autonomous vehicle. Maybe you can change the flight deck and so forth, and that can change how we configure. But it can also mean In fact, another panel session earlier this week on the future of design brought up this idea that perhaps greater automation and perhaps some even autonomy in the design process can make that whole, both make the process more efficient, but I think open up also the design space. What's possible for these future vehicles and future configurations? So that could be a part of what comes out of advanced vehicles. Integrated Aviation Systems, Ed Wagner's program. What it really brings to the table is, for all the thrusts, the ability to take some of these really difficult problems that require integrated and complex research systems in a flight environment and put a projectized and focused emphasis on that. So right now, and Ed will describe this, doing that for UAS and the NAS, and we'll continue to provide flight research and focused opportunities that'll advance autonomy in cooperation with the rest of the programs. And then finally, Doug Rohn at the end is the Transformative Aeronautics Concepts program, and that's taking a very different look, saying let's look at new concepts, new ideas that aren't really in the perhaps on the roadmap right now or the roadmap that's being developed, but let's take a look at these. Let's look at some different ideas, and let's do some fast feasibility, a couple of years. Let's see if these ideas are feasible. If they are, we can get them into the roadmap, into the programs. If they're not, we'll learn from it and we'll move on. But I think that idea of fast feasibility, fast innovation is particularly pertinent to the autonomy thrust, where there's such a wide open opportunity to explore and to innovate in that space. So it's going to be a critical component of our planning as it evolves and moves forward. So with that, that's it for me, Sanjay. I can turn it over to John.
Right.
Great. Bob, thank you. Yeah, most of us have very pretty cover charts here, so I'll give you a chance to focus on that. At any rate, I have a few more minutes than my colleagues here, in part because, as Bob mentioned, I'm going to be taking some time to put some context around some of the work that we have sponsored or conducted over the last year or so to help us in understanding our address of our strategic thrust around autonomy, but also take a little bit of time to talk about the substantial elements of the new AOSP program that I'm overseeing, and the way in which we're taking some early steps in order to step up to elements around system operations and safety and autonomous operational capability that we can begin to take some steps on early. So before we do that, I want to start by establishing a premise. And frankly, this is a premise that was behind all of the work that Bob had talked about in terms of our strategic planning, and why, in essence, we have that strategic thrust 6, which is the transformative autonomy for aviation. And it comes as follows. So first, as premise, we believe that autonomy is needed because we are confronting human cognitive performance limits to improvements in safety, mobility, and efficiency of the aviation system, and an aviation system that, as Bob mentioned, is continuing to leverage much higher demand on the need for air travel, and again, those limits are causing some significant barriers to growth as we see going forward. We also accept that autonomy can overcome these human limits and enable applications, functionality, and performance that are not possible today. And we accept this because we know that it's been supported by the history of technology and automation advances that have overcome prior human cognitive performance limitations. So as we stand behind those premises, we look to address strategic thrust 6 in terms of the steps that we need to take in order to outline our ability to address those premises and the implications that come from that. So establishing initially a dedicated long-term research plan, a research that that's organized around technical challenges to achieve midterm and long-term outcomes is going to be the major drive for strategic thrust 6. When we talk midterm, we talk long-term. We're talking, the 2025 timeframe for the mid, 2030, 2035 for the long. So it is have long legs on these capabilities. That doesn't mean, however, that we don't have efforts that we're driving in earlier stages, even near term to early midterm, that are serving to complement that. And some of the complements to that long-term research, are addressing some near-term challenges. For example, some of the work that you'll hear as my fellow PDs talk in a few minutes, the UAS integration in the NAS in EDS program, and even UTM or UAS traffic management work, low altitude airspace management capabilities for small UAS in my area are examples of how we understand that full autonomy challenge is a large one and is a distance off in the future. We still see that there are precursors and essential research and development and application elements that can feed that, and those do also remain part of the program and aligned with our strategic assured autonomy for aviation transformation thrust. But we also see that we need to continue to develop certain capabilities that will allow us to act on these near, mid, and more important farther term capabilities in terms of something such as the LVCDE, the live virtual constructed distributed environment, that can be a key component to evaluating these new concepts and these new approaches and technologies in autonomy that allow us elements of real world test environment. Parts of that are looking to be integrated into advancements in SmartNAS, and I know I'm giving you a number of acronyms now. I will take some time later to talk a little bit more about that additional modeling capability, which allows us to look at wholly new architectures in novel ways that are critical, that allow us to evaluate the autonomy modeling and simulation, look us to do interfaces with autonomous vehicle and other subsystems for modeling and simulation that cover the breadth of work that we're doing in ARMD. So as I mentioned, I'm up front here talking a little bit more in part because I'm setting the stage for some of what you're going to hear as we go down the line here around systems development, around vehicle development, and around some new concept opportunities and transformative opportunities that will lie in other parts of the program. Actually, I'm back. I want to talk about a little bit how we are coming to begin to populate our structure in the Mission Directorate and our address of Thrust 6, building off of what Bob had talked about a few minutes ago in terms of these, the external study efforts that we did. As he mentioned, we just recently, in the last year, I believe, completed the work under NRC. We sponsored that work, but certainly it was a national effort looking at autonomy research for civil aviation. It was a study that looked far beyond simply NASA's opportunity to contribute to that, but truly a national view. We found great value in bringing together that part of the community, those technical experts covering the breadth of capabilities across the U.S. in terms of technologies and opportunities that can contribute to autonomy. And they provided us some very, very valuable input that was allowing us to help establish some barriers and some challenges that we could step up to. But then similarly, in roughly parallel effort, we convened an internal NASA group, the Intercenter Autonomy Study Team, to begin to look at where NASA has the opportunity to address some of these major challenges and what are the things that we can step up to within our partnership capability and within our internal capability in order to meet some of these. And what we are looking to do now, what we're in the process of doing now, is merging those two efforts, understand where the common ground lies, and to begin to develop, in the process of developing an integrated, prioritized set of research themes and challenges. But before I do that, let me talk a little bit more about those two studies and some of the kind of the overreaching and overarching comments and observations we took away from them. First, the NRC scope, being that it was all of civil aviation, was a little bit different. In some way, people may say somewhat less ambitious, perhaps, than what we had conducted under ICAST. NRC was focused on what they referred to as increasingly autonomous operations. a condition where there are assumptions in terms of the role of human that will be maintained throughout continued evolution of that system. Not to suggest that transitions from where we are today to much more fully autonomous, futures aren't necessarily addressing a continuously autonomous future and path, but certainly it's important to understand the challenges that may place on the nature of autonomous architectures for operations and for vehicle use that may be discounted as we look at increasing autonomous ops. So the sort of thing that we need to do and will be doing as part of our work is not limiting exclusively to increasingly autonomous, but rather a full autonomous view. The NRC study was also somewhat a bit more narrow technically. They had a strong emphasis, not exclusive, but strong emphasis on vehicle operations perspective and the vehicle's role in that. Clearly, vehicles are the driver, are the mechanism by which we bring the art of transportation to meet the demand. But the system elements of that, allowing new vehicle operations, autonomous operation to act in a more efficient, safe, and effective autonomous operational system, autonomous NAS, is where we're also spending some time. But as much as I do say that perhaps they may have been, in our view, what we could describe as a little bit less ambitious, they certainly were a bit more expansive in other areas. And they addressed elements of policy and legal challenges that were critical for us to understand and view as we go forward. Overall, there was very good agreement between what the NRC barriers are that you saw Bob present on several charts ago, and what the ICAS research theme areas are. They're in small print, but I'll talk a little bit more about that on the upper right side of that chart. But the comparison between the critical elements that the NRC laid out and where we viewed those critical elements were nicely done and actually showed an awful lot of commonality. And the NRC actually also had a couple of key insights that ICAST didn't develop as well in the work that they had done. Major example is advancing the science of modeling and simulation for autonomy, the use of modeling and simulation as part of real-time operations or real-time data gathering, digital twin opportunities. So I think we have two very good bits of work covering a tremendous common area of study and opportunity, and opportunity for us to build off of that in order to build what I refer to at the bottom of this chart as our internal autonomy research roadmap that will address these barriers and these challenges. Again, some of those specific barriers that we looked at, some of those challenges, V&V and certification of autonomous systems, system-wide status and assessment of the operations in real time, test and evaluation capabilities, as well as autonomous vehicle control for elements such as health management, adaptation optimization, and clearly autonomous planning from the system side, scheduling and interoperability are all things around which we know we have some clear capabilities and are looking to build leadership roles with the broader community in terms of establishing our contributions to midterm and farther term capabilities there. There are other areas on the right side of that upper right-hand chart that we have there that are areas around which our leadership is certainly something much more balanced with a considerable capability in the external community. Real-time vehicle-centric cooperation, interoperability, human autonomy teaming, and design and analysis of autonomous systems are some of those areas for which we do have strong capability, but there are tremendous assets and organizations that are driving very, very large contributions to these areas out in the field. We want to make sure that we are leveraging that. We are working closely with that in order to be able to take advantage of it as we build our capabilities in the programs in our EMD. And certainly on areas that we watch, areas that, again, we are not uncommitted to in terms of our internal capability, but for which there is tremendous work outside that we want to be pulling in to much greater degrees. Secure command and control and autonomy infrastructure and information management fall into those areas. So as we have gone through this process, we have been establishing strong capabilities and strong understanding of our work and paths we need to go forward that we think are necessary, that we know are necessary based on these studies and external partners in order to meet that need. And we'll be looking to build this roadmap, this long-term roadmap, to answer these questions, either as part of our internal effort, and certainly that as we grow with our external partners, and also to demonstrate high payoff integrated applications that can advance the safety and the efficiency and the flexibility of the NAS, bottom line for increasing competitiveness of the U.S. civil aviation industry. That frankly is the bottom line for so much of what we're doing in autonomy, and the potential that we see for these that will allow us to be able to do that. So I want to end with one more, or end this part with one more kind of overarching task, if you will, that I think we need to take on as part of this. And when we look at where we are today, the known world of our problems, our challenges, and our capabilities, we have some rather deterministic models and capabilities and processes that allow us to function well within that. It doesn't imply that there aren't uncertainties and there aren't complexities, but we have this well modeled. We understand how decomposition of those capabilities for the incremental parts of the overall system, vehicle, and operations are managed. We understand how to manage risk, and we deal with sensing and matching of data in order to be able to evaluate our progress either in safety or in performance. Where we need to go, however, is a much more discovery element of a future world and future operation and vehicle capability. We're dealing with many more unknowns. We expect to have emergent and machine learning capabilities. We will be a far more networked system. Again, I talk discovery and I talk exploration of space and operations and missions, where we are learning and dealing with probing and making sense of capabilities in a much more probabilistic fashion. How we go from our more deterministic and complex world to a level of complexity which adds additional elements of discovery and emergence is going to be that critical autonomy technology barrier that we need to cross. Bridging this barrier is going to require that we focus on coordination across the system, rather than simply distribution of knowledge, increasing the information, the intelligence of individual actors. This needs to be a system view. This needs to be a networked, common understanding and system approach, not just an individual capability improvement. So I mention this as kind of an overarching element to the way in which we're going to be addressing those future barriers and those technical challenges. So let me now change topics a little bit here and point to our work in airspace systems and give you a sense of how we are stepping up to the Autonomy Thrust 6 within airspace operations and safety. As Bob mentioned, this is a program that is bringing in the ATM and the automation decision support tool work that we have been doing in support of the FAA for so many years in the airspace systems program, with the system-wide safety, real-time system-wide elements of safety management of systems and vehicles that Doug had driven through the safety program earlier. I think it's an exciting bit of work that brings together two critical elements. You see on the left-hand side there the projects that we're doing in there. We are doing those that cover a full time frame from near term to mid. Bob talked about Thrust 1. We have a coverage of Thrust 1 through the airspace technology demonstrations, but what I'm going to talk to you today about the other two projects, our safe and autonomous systems operations and our trajectory-based and our SmartNAS testbed work that are working to build capability, leverage each other's talents in order to make progress on our Thrust 6 work. Part of that is going to be our need to move towards this autonomous future. And if we look at, and I'll take this from the ATM, the air traffic management perspective, if we look at where we are today, we have clearly our current generation is a human-dominated system. We're dealing with controllers that are managing aircraft by segments, handoff from sector to sector. in a way that puts some inherent limitations on the ability to manage our airspace and flow of traffic simply because of the constraints of people and communications. We're working now, as we have been for a number of years, on that next generation. Consider it next gen as the FAA has defined it to date, but one at which decision support tools, still a human-centric based decision support tool, are allowing us to provide through ground-based capability opportunities to do more time-based management and even some cockpit avionics capabilities that are allowing us to bring more benefit to the system by means of support, decision support, or automation support to controllers. Where we need to go is in a generation beyond next gen and even beyond what next gen has been thinking about in terms of areas of autonomy. Looking to do far more automation and integration of that for what we refer to as TBO, trajectory-based operations, gate-to-gate trajectories that are not segment-based and handoff, controller-to-controller efforts that will require air and ground capability, where intelligence on the aircraft is allowing management of flights by their capabilities that don't need continuous oversight in ways to provide that efficiency. But certainly, looking beyond that for the far more autonomous future in an ATM plus 3 environment, if you will, where a different architecture may entirely be necessary in order to take advantage of autonomous ops. Machine intelligence can be a part of that, and this autonomy path, this progress is where we need to be moving and addressing. So developing concepts, algorithms, and technologies and architectures towards ATM 3, ATM plus 3 is part of this autonomy process. Validating key phase transitions as we go from these generations of technologies, make sure they're feasible, safe, and assured. Analyze benefits and ensure overall autonomy architecture compatibility. We can't be dealing with individual autonomous capabilities that don't fit in the autonomy architecture, which will be different than NASA today. It needs to be seamless. We need to develop and validate and migrate towards this architecture, supporting safe autonomous operations. Real-time system-wide safety is going to be critical. And certainly transition these safe and beneficial technologies to stakeholders for their operational use is going to be, again, the key focus of what we're doing. In terms of our program hypotheses and challenges, future operations, densities, and new business models, just think UAS as an example, can't be safely enabled today. The current designs are human-centric, and those operations simply can't allow that kind of growth and the demand that's required. Some of the challenges that brings are the current human-centric architectures aren't scalable. Future architectures need to safely enable autonomous operations as needed. The autonomous technologies in nominal and off-nominal conditions need to be able to show the address of novel circumstances and exception by management or management exception situations. Certainly, the readiness of machine intelligence in those base systems are not where they need to be. It's a challenge to meeting this autonomous future. Roles of humans continue to be a concern, whether they are in the loop as they are today as we transition to, or on the loop, or in a more management role. We need to understand how they engage with these autonomous operations going forward. Assurance and acceptance, confidence and trust, if you will, these autonomous operations technologies is a key concern that we have to address, as well as these the auto enablers, due to complexity, diversity, and demand, need to address cost pressures and be able to allow us to provide real benefit to the system. Again, not just FAA and government users, but certainly to the users and the operators itself. So in my last couple of charts here, I'm going to take a minute to talk a bit about the Safe and Autonomous Systems Operation Project, how it's stepping up to at this early stage, still under development. One thing that Bob hadn't mentioned is that AOSP, IASP, AAVP, and TACP are just beginning. This fiscal year, in fact, in the last several weeks, we finally got the approval to go forward. So much of what we have to talk about are things that we are still developing. But in SASO, we've been spending time to think about this over the last year. We're building a project plan in order to address this. At the bottom of this chart, you will see the foundations upon which all of what we are doing is built in terms of our autonomous address. It's coming from the perspective of establishing an autonomous operation architecture that'll enable this increasing autonomy. As mentioned, we need to make sure we have that architecture in order to ensure that any capabilities that are brought in meet that framework and allow us to see those benefits now and going forward. Similarly, foundational V&V and certification issues are going to be critical. The challenges that the NRC brought up in terms of policy and in terms of, what were the words they used? Legal perspectives are certainly a challenge. Elements of certification and the foundational support for assurance in V&V is going to be critical to anything we do going forward. However, we are also looking to define and work with the community and work with across programs in order to build capabilities that we can insert into that autonomous architecture. Autonomous airport ops, terminal airspace are key elements that have opportunity in order to bring autonomous operational insights and technologies that allow users and airports to bring capability and save time, resources, fuel, and address some of the other environmental challenges that were brought up by Bob in terms of our overall strategy. UAS is another big part of a challenge and a drive for this. You'll see in a banner across the bottom, enabling low-altitude airspace operations. That's code for a capability that we're developing called UTM, or UAS traffic management. It is an exciting area of interest we have with the UAS community around building low-altitude airspace operational environment, allowing carriers to build repeatable business opportunities and safe opportunities around operations for small UAS, package delivery, surveillance, agricultural methods, and a variety of things that the community is clamoring for. The vehicles are there. Is the system within which they need to interoperate that isn't? We're looking to help define that and set up some really aggressive capabilities. Certainly, as you go to the top of the chart and the higher the high altitude efforts for autonomous aircraft, reduce crew operations and autonomous traffic flow, have some additional challenges that we're looking to step up to. And within these areas, these are not areas that are exclusive to SASO or AOSP for that matter. Certainly Ed's work, which you'll hear about in a minute, in his area with UAS in upper altitude and airspace transition to Class A and Class E operations, have some capability we need to bring to this. From the vehicle side, Jay's program, and certainly even looking for new innovative operations and business models and capabilities, Doug's work in TAC has certainly a role that we want to make sure we're addressing. And my last chart here before I pass the remote, actually I go two, I'm sorry. As we look at the way in which we are approaching this chart is pretty much just kind of summarizing what I had mentioned before. Overall architecture is the center. We build concept of operations for those autonomous operations. We build targeted capabilities, and we conduct studies and simulations, tests, and demonstrations in order to validate that in that architecture. And again, this is addressing the overall roles of machines and technologies that need to be compatible moving forward. These connections are going to be critical to doing that. And as just one last bit of insight, I mentioned earlier by acronym SmartNAS. SmartNAS is the third project in the program. Shadow mode assessment of realistic technologies for the NAS. It is, in essence, a test bed that allows us to evaluate a variety of new architectures that, frankly, are not possible to evaluate in the system today. A fully autonomous operational capability. If we had that system, we could not evaluate, we couldn't evaluate it today in the system because the structure, the airspace, the center-based approach to managing traffic does not enable the system to be dropped in a way which real evaluation can take place. We're looking to build this sort of capability around distributed evaluation environment, bring in real shadow mode assessments to bring in real data, but run that real data, run those real operations in a new architecture. It's going to be critical to anything we have going forward with autonomy and the work in SASO. Similarly, real-time system safety modeling, taking advantage of some of the data mining and prognostic techniques that we've done through Doug's program in safety earlier, are key to being able to evaluate some of the discovery of precursors that can impact our safety of these new operations, and the safety assurance technologies around elements of V&V and other capabilities are also going to be critical. So we have a strategy at the top end. We've reached out nationally in order to help us get some insight into some of those key challenges. We've done some internal soul searching to understand where our capabilities lie. We're beginning to work across the Mission Directorate and the centers in order to build a roadmap that can address that. And from the Airspace Systems, Air Operations and Safety Program, we have some content that can leverage that. But at this point, let me turn it over to Ed, who will pass down the line to provide some insight into ways in which the rest of the programs and ARMD content can feed into this.
So thanks, John. As Bob kind of laid out the overall strategy for the Mission Directorate leading down to the autonomy thrust, and then John talked a bit about two things. One, how we'll take the information that we have around a couple of different studies and lay out a roadmap, and then how his program is supporting that. I wanted to spend a few minutes talking about the Integrated Aviation Systems Program and the work that we're doing and how that supports the autonomy work as well. But first I wanted to give you just a very, very brief, quick overview of what IASP is all about. If you look over on your left, we've got the ERA project, which most of you may be familiar with this. Faye Collier is here as our project manager. The first iteration of a real focused program in the Mission Directorate started in 2010. It's entering the last year of the project. And Faye has put together a team that in the areas that are listed below ERA, airframe technologies, propulsion technologies, and vehicle systems integration, will be delivering on technologies which have been validated through 8 very complex integrated technology demonstrations over the life of this project. So it really shows a great effort on the overall NASA family's part of meeting some aggressive fuel burn, noise, and emissions goals. Over on your right, the newest project that we have in IASP, called Flight Demonstrations and Capabilities, this is a reflection of the desire from a Mission Directorate point of view to embed flight research in all phases of our research, not just a culminating end-all activity that at the end of some project. And so it should be an integral part of all the technical planning that we do. So to enable this, we're going to have to focus on innovation and flexibility. That'll be critical as we do our program planning. And so we'll be importing good attributes of both NASA's X-plane culture as well as best practices in industry to do this, and particularly relative to frequent flight demonstrations with very disciplined schedules. So each of those fits into the work that we're doing in IASP in a unique way. But the flight demonstrations and capabilities work certainly will be there to support flight work associated with validating key autonomous concepts or technologies that support autonomous operations. Now, the UAS and the NAS project, which really preceded both the restructuring of the Mission Directorate and the work that we're doing on autonomy, but it does set and form a foundation for much of the work that will be done in the Mission Directorate. This another focused effort, a 6-year effort that began in, went through formulation in October 2010, began working in 2011. So they're in the second phase of their work, and we're going to focus on the work that they're doing and how that relates to an overall autonomous roadmap in the direction that we're going in the Mission Directorate. Now, this graphic, which actually has a basis in enterprise architecture called Operational View 1, while it looks like a cartoon almost, but it does represent all of the key tenets that we're working in the UAS and the NAS project. We're working sense and avoid, that is how to maintain safe separation without a set of eyes in the cockpit, as Jim Williams likes to call it, our Mark I eyeball. Since you don't have that, how are you going to ensure that you have safe separation? Command and control, how to provide robust and secure communications with the vehicle from a ground control station. We have human systems integration, the design of a ground control stations and the attendant displays associated with that for the pilot in command. How do you do that in order to safely maneuver the UAS in the national airspace? And how do you do that to make sure that you're operating in a very similar manner as a manned aircraft so that it's not an additional burden to air traffic control? And then tying these technologies together is our integrated test and evaluation. How do you test these various technologies in an integrated manner in a relevant test environment so that those findings are accepted by the regulatory community readily, and that the design of the experiments are done such that those findings are valid. Now, everything that we're doing within this project is not captured under those technical challenges. We're also doing some other work. Down in the lower left-hand corner, you see a small little vignette called Small UAS Mission Support Technologies. What we're representing there as an example is a fire spotting mission that we recently accomplished in the Great Dismal Swamp in association with the Department of the Interior. Another example down in the lower center part of the graphic is UAS restricted use certification. So can you certify aircraft, unmanned aircraft, for only restricted missions? John talked about the UTM. One of the missions that could be done under UTM would be precision agriculture. So would the community be able to certify certain unmanned aircraft just for that type of a precision agriculture mission? So we're also doing work in this area as well. The next graphic that we have shows a flow down from this autonomy thrust down through specific outcomes that we have for autonomous applications relative to integrating unmanned aircraft into the NAS, then to the goal for UAS in the NAS, which is to provide research findings to reduce some of the key technical barriers associated with routine integration of unmanned aircraft into our national airspace system. We have two research themes under that. One for integration, that's where our sense and avoid work falls, our command and control work falls, and our human systems integration. And then another has to do with the test infrastructure. Jim Murphy, sitting in the audience, is leading that work, putting together, John talked about our LVCDE. Part of what he's doing is maturing the technologies associated with that. And then the technical challenges that we have, we've focused those very keenly on the work that's being done in RTCA, and in particular, Special Committee 228, looking at a couple of different phases of unmanned aircraft system operations in our national airspace. The first one has to do with defining what the minimum operational performance standards are for a unique scenario. That is transiting Class E airspace, if you think back to the chart that John showed, transiting Class E airspace on its way up to interoperating in Class A airspace with other manned aircraft. So what are those unique challenges? What are the unique operational performance standards that need to be addressed? That's phase one that's being done in RTCA Special Committee 228. And then there's another phase which we're not supporting, but we're advocating the support of that in a follow-on effort, which will be done in a highly focused manner, but another really unique scenario, which will be the interoperation of unmanned aircraft along with manned aircraft in Class E airspace. So what would be the minimum operational performance standards for that type of scenario? So if we dig a little deeper into the technical challenges that we're addressing, We'll take these one at a time, starting with our sense and avoid performance standards work that we're doing. So we're looking to provide research findings that will help not only develop but also validate the UAS minimum operational performance standards for sense and avoid performance and interoperability. The team has done a lot of work just in fiscal year 14. We participated in an integrated human-in-the-loop test series. We executed an unmanned aircraft controller acceptability study where we were looking at how a pilot in command of an unmanned aircraft would interact with air traffic control. And would the air traffic controller find that acceptable from their point of view relative to the timing and response to commands that they're given? And then participated in a part task simulation on traffic display evaluations as well. If you go just below that, our command and control performance standards, we're looking at terrestrial command and control work. We're looking at developing and evaluating, along with Rockwell Collins, a prototype communication system, a radio. We're going through several generations of this. We've flown the second generation for traffic generation in association with our sense and avoid work for that. We've taken receipt of the third generation prototype radio. We've put the plans together and done the initial flight testing for that third generation radio as well. This work is being done at Glenn Research Center. Tremendous progress is being made, and this is all being made within the allocated spectrum for unmanned aircraft operations and command and control for them. And then I alluded to the ground control station and the displays associated with that. That's under our technical challenge that we call human systems integration, looking at both how the pilot in command interoperates with the ground control station and what displays give them the best information, the most pertinent information, so that they can safely control the unmanned aircraft in high density operations within the national airspace system. Again, another series of integrated human-in-the-loop tests were done during FY14, executing a couple of part task simulations in FY14 and supporting the other flight research work that's being done as well towards the development of a research ground control station and ultimately guidelines that will go to RTCA 228 for our ground station design. And then finally, our integrated test and evaluation that I alluded to. John talked about our live virtual constructive distributed environment. This is the initial instantiation of that work that we're developing and evaluating along with support for all of the flight work that's going on within the project. So this gives you some sense of the intensity of the work being performed in the UAS and the NAS project. Over the final 3 years of the project, the preceding year, FY14, and then 15 and 16, we've got an intense schedule of simulations and flight research that are going on. We just finished our integrated human-in-the-loop simulation work back in the summer. We finished in the first 3 months of FY15 our initial flight test for evaluating a sense and avoid algorithm for unmanned aircraft along with a due regard radar. And then the work from both the simulation and that flight test will go into our flight test 3 and 4 series, which will be done in FY15 and 16, validating the technologies that are coming out of the various work that's being done within the project. We've done we've attempted to look at how far will we get towards all of the work that needs to be done within in UAS and the NAS relative to routine access for unmanned aircraft into the national airspace. Now this is all done in-house. It's it's certainly not a scientific approach, though we took a very structured approach and repeatable approach on how to do this, looking at all the needs, making an assessment of how far we in UAS and the NAS will go along towards meeting those needs, looked at the work that's going to be done in UTM and John's program relative to that, and then the work that's going to be done in industry. So that you can see against a number of different attributes that we're going to make a lot of progress, but it certainly isn't everything that needs to be done. While we will have finished the phase 1 MOPS, they'll still and have initial human factors guidelines for our ground control stations. We'll do an assessment of the test sites, how the FAA's test sites can work with us and we can work with them. Some initial operating rules for visual line of sight, small UAS operations. There's still a lot of work that needs to be done. And we've done an assessment of that work as well, what needs to be done beyond FY16. And so this is our assessment of some of the remaining gaps at the end of this project that still need to be done. Some of this relative to routine access, some of it has to do with autonomy and where we need to go within that. So the phase 2 MOPS we've called out, certifiable technologies, making sure that the technologies that we're working, we've got certification procedures in place for those, interoperability and next-gen compatibility for the technologies that we're working, safety standards, airworthiness standards, test and evaluation guidelines, V&V techniques for autonomous aircraft, and then addressing some of the social concerns along legal privacy, noise, safety, trust issues that still have to be done as well. And there's a lot of work that NASA and the capabilities that the men and women that we have at our research centers can bring to this, and I've just articulated some of those there down in the bottom part of this chart. So in summary, execution for this initial instantiation of autonomy under our UAS and the NAS project is well underway. We're achieving tremendous results towards the project's goals. We've got a very aggressive schedule of flight research over the next 2 years, the final 2 years of the project. This is focused laser sharply on RTCA's SC-228 work, particularly phase 1. We're advocating to continue some of this work focused on RTCA's phase 2 work, which is a very interesting interoperability scenario in Class E airspace. We feel like that this work is paving the way for near-term integration of highly automated civil UAS into the national airspace system. But as we just pointed out, there's still a lot of work that needs to be done. So a lot of milestones along that roadmap that still needs to be addressed. But we do think within UAS and the NAS that we're making good progress and we're ready to continue that work and continue bringing those capabilities towards the autonomous roadmap. So with that, I'm going to pass it over to Jay Dreyer.
Okay, thank you, Ed. And I will skip the title slide and go straight to talking about the Advanced Air Vehicle Program. Just like you've heard mentioned several times, this is a relatively new structure, just in a matter of weeks that we've officially been operating in this new structure. And while it's been familiar to most of us sitting up here because we've been working on this for some period of time, I don't want to assume that everybody's just familiar with that. So I thought I'd start off by setting a context of what do we mean, what is the Advanced Air Vehicle Program, the type of things that we work on, and where we're going, where the focus is. And anybody that's familiar with the work that we've had within the Aeronautics Research Mission Directorate is probably familiar with the Fundamental Aeronautics Program, and there's a very strong heritage to what is in the Advanced Air Vehicle Program to fundamental aeronautics. You'll see much of the work that will continue has a lot of the same focus, but there are a number of key differences as well. The other thing that the new strategy has really given us more of a long-term focus and has really helped define and shape the portfolio and help show where that emphasis is. And so for Advanced Air Vehicle Program, you saw those 6 thrusts that Bob talked about earlier. We have very strong alignment with several of those. So thrust to the innovation in commercial supersonic flight. We've been working on this area for some period of time, made some significant advances to possibly opening up the potential for overland supersonic flight as a key area that we've been looking at. For Thrust 3 is probably one of the largest areas across the entire mission directorate. They'll look at the ultra-efficient commercial vehicles. And several of our projects have a very strong alignment with this, looking at improved efficiency, improved environmental characteristics, and so on and so forth. So probably one of the largest thrusts that we have. And then the relatively new, the Thrust 4, the transition to low carbon propulsion. And it was actually a lot of the work that came out of fundamental aeronautics, some of the advanced concept studies that really paved the way and opened the door to do some of this work and look at some of the potential alternatives to traditional propulsion, for example, that might lead the way to doing some things in a much different manner than we're used to today. So that's one of those areas that's certainly growing. But if you would look back, autonomy really wasn't a major key focus. And I think this is one thing that the strategy has helped give us a little better of that laser sharp focus on the areas that we really need to look at going forward. Another key area that's different, and we didn't talk too much about the transition from the old program structure to the new, but some things that have also changed. We no longer have a single program dedicated to the capabilities. And so Ed alluded to it with the flight assets that will be covered, but for the ground test capabilities that were covered by the Aeronautics Test Program have now been folded into the Advanced Air Vehicle Program so that we can even better align those with the research needs that we have in the future. And another key area, of course, was the work that was done in the Aviation Safety Program. And so safety now needs to be something that we don't count on another program to look at the safety aspects for the work that we're doing when we're addressing things like efficiency or environmental performance. It's got to be an innate part of what we do. And so that's another critical element that's going to define what the Advanced Air Vehicle Program. So just to give you an idea, it's easy to think of it in terms of the projects, and you'll see a lot of similarity in some of these and some that are new going forward. You see those listed on the right-hand side of the screen right there. The Advanced Air Transport Technology project, one of the largest with a focus on especially that Thrust 3 area, but also the Thrust 4, the transition to low carbon propulsion for our transport or fixed wing type of applications. And you see the revolutionary vertical lift technology. This continues some of the work that we had started in rotary wing, but looking at where can we open up the world to the unique capabilities that are enabled by vertical lift. And again, some of those very strong issues that we have to overcome in efficiency and environmental barriers, in particular noise, when it comes to that. I talked earlier about our focus on Thrust 2 with the innovation in commercial supersonic flight. We've got a project, the commercial supersonic technology project, that's lined up directly to deal with those challenges and open up that potential for new opportunity. Now, something that is new to us is the Advanced Composites project. That was something that was started under Ed's leadership, and we've now basically taken that over, and we'll take that also to graduation. This is one of those projects that does have a specific end date, but the idea is how can we advance our ability to introduce and bring some of these new materials and certify them for use much sooner, much more efficient than we've been able to do in the past. And then finally, we've got this Aeronautics Evaluation and Test Capability project, and this is where we're bringing in some of that work on the capabilities asset, and how can we work with that and better align that with the research portfolio, but also make sure that we're keeping on to those same strong practices that were developed under the Aeronautics Test Program to maintain those type of capabilities and expand those. And so that gives you an idea of the kind of suite of projects that will be under Advanced Air Vehicle Program. The other thing, and you heard a little bit some of the discussion too of the terms of the technical challenges, and I'm not going to talk about specific technical challenges because most of those are lined up to the other thrusts, and we're here to talk mainly about autonomy. But I wanted to stress the fact that one thing that we really emphasize with these technical challenges is the multidisciplinary nature of these. And so one of the things, when I sat back and looked at it and said, well, I'm not really, when I look at the portfolio that we have, where we're transitioning from fundamental aeronautics over to Advanced Air Vehicle Program, I'm like, we don't have an autonomy thrust right now that's dedicated to that. But when you look at the portfolio, there's a number of areas where autonomy actually is embedded within the portfolio itself. There's areas where we're actually doing that work that's part of the portfolio today. And I'm not going to talk about all of those and give an example of it, but I did want to emphasize that it's not like we're starting from scratch, even within the portfolio that we've taken over, and that's because of that multidisciplinary nature of the technical challenges. So I'll give you an example. We've got some that are working on new airfoil designs or configurations, high aspect ratio wings, looking at lighter structures where we're not dependent necessarily on the structure for gust load alleviation, but can the control system do this? That, when you look at it, in depending on how you draw the control volume, it could be considered an autonomous system for the gust load alleviation. We don't always think of it that way, but really that is part of the portfolio that we have that we're looking at. But when you take a step back and you talk about specifically for autonomy, really where are we in the roadmaps? And one of the things I've got an advantage being last, but also because John's leading the effort within this road mapping, and he's had a chance to talk about much of this, so I'm not going to try to repeat what he said. But we're definitely working very closely with the other programs. So, I mean, all 4 of us are working together, but really under the leadership provided by AOSP to help pull this roadmap together. We're really at just the beginning stages, though, to say where we are. We have not made a lot of progress as far as pulling that out and also defining what are the next challenges. Because one thing and one term that I really like that came out of some of the studies and some of the work that's come already is, one, there's also, you can just look at it, what is the definition, what do we mean by autonomy? And you could ask 10 different people and probably get 10 different definitions of what we actually mean by that. And we talk about automation and different terms that are really more specific to describe it. But the way that was also posed is it's not like we're going to turn a light switch and we're going from a certain mode to all of a sudden everything is autonomous, but we talk in terms of the increasing autonomy. And I think that's really true and a really good way for us to think about it, that it really is embedded in parts of the research portfolio that we see today. But what else do we need to do? How else do we need to look at this problem as we continue to grow? Where are some of the common denominators that we need to consider? And so fortunately, we're not starting from scratch, even from the vehicle perspective. We've got a lot of things to base on, the work that was done from the NRC study and also from the internal effort, the ICAST study that was mentioned in discussion before. And I think there's a number of elements, a number of threads that we can pull from that are going to have an impact when it comes to the vehicle side of what we need to do. And also looking to the work that that Ed just described, the UAS and the NAS project has, they've been taking a more focused look at this, and that's also opened their eyes. Well, we're working on this, but hey, this also might be a challenge and other things that we need to consider in the future. So we're talking to the people that are working on that effort. The other thing I really wanted to make clear too is, so clearly there's an opportunity where we may need to grow, we may need to expand some of the work that we're doing in autonomy within the Advanced Air Vehicle program. That doesn't necessarily mean that everything starts within this program itself. And you're going to hear from Doug next, but I definitely wanted to plant the seed early to think about how this new structure will also function as far as the creation of new ideas or coming up with new innovative concepts. And as the mission programs, we have to be very aware of that. And so we're already looking to the Transformative Aeronautics Concepts program to develop and determine the feasibility of some of these ideas, and then we create the ability to take some of that knowledge for things that are successful and show promising for further growth, and then build upon those. So everything that we do or what we try to incorporate into this new plan may not start directly within this program, even if it is vehicle related. It could be something that starts over in the Transformative Aeronautics program itself. And so when we think about, what do we mean by autonomy or what are we doing? One thing is clear, we're not doing autonomy research just for the sake of autonomy. What is the purpose and where does this eventually have a meaning or a purpose? And certainly within our program, there is a strong pull from the other thrusts that we're already working, especially I think in the thrust 3 and the thrust 4 area of where there's a potential for where autonomy can continue to have benefit. And in some of these areas, and I've got, and I list just a few things on the chart here that might have an impact. And I'm very clear, it's certainly not limited to this very short list. But there are areas like safety, some of these new configurations. Maybe there's autonomous concept that can help ensure the safety of the vehicle, that we haven't really thought about or imagined or looked at the problem that way before. The same thing for efficiency. A lot of the work that we've done is driven to higher efficiency. I even gave an example where some of that work has already been incorporated into some of our technical challenges. How else can we expand? How can we think of it in terms of that? And then Bob mentioned and alluded to the last thing I have on the slide here is from the design process itself. Are there things that we can automate within our tools, even greater to the extent that we've done today, that helps with the process of designing new vehicles and how we will incorporate those? But besides just looking at the vehicle itself, we also need to think about how those vehicles will be used. A number of missions, there's a very wide trade space when you think about it and where the application can be. And at some point, this list of things that we can do certainly grows very, very large. And at the same time, we also have to look at this within the perspective of the rest of the portfolio. It's also important that we do. But also ask ourselves the question, where can we have the most impact from NASA? We don't need to be playing catch up. If somebody else is already working an area and that's well in hand, that's not necessarily a reason that we also need to get on board with doing that exact piece of work. How can we leverage that and move on? So I like to think of it as there's a lot of things that we can do, but what are the things that we should do? And that needs to be an important part of the process as we're pulling these plans together and bringing everything together. To evaluate what it means to be part of that autonomy vehicle roadmap. So with that, I'm going to I lay out something and I would like to highlight this potential decision process. I'm not trying to say that we've got a specific team that's already been defined that has a very narrow purpose or focus of what they're trying to do in laying out this vehicle roadmap. But instead, I'm using this to highlight some of the concepts, some of the things that have been true of most of the planning that we do for our research portfolio, but it'll also be true when we talk about what it means to develop an autonomy roadmap for vehicles. And understanding what that community needs. What's the drive? What's the pull? Why are we doing this and why is it important is certainly a critical step in doing this. And then ultimately, how do we go through those filters, map those to the specific needs, and really that hard process is then how do you prioritize that? Because we're talking about a large list of potential areas where we could work. There's a number of research challenges in this area. I think that's been clear. You've seen not just in the presentation today, but there have been many presentations throughout the forum this week that have talked about the challenges in the area of autonomy. But ultimately, you do have to prioritize that and match those to the skills and the available resources to do the work. And then at the end of the day, then helps define what that portfolio, and that's not a one-time thing that you've gone through and it's done. You have to continuously reevaluate that as things change, because after all, what we're doing is research. We're expecting to learn things along the way, and that should change the direction that we go. That should be part of the business that we're in, and I think we've got that right kind of attitude and that mindset as we're going forward. So from a vehicle perspective, we're really at the beginning stages of this. We're going into this eyes wide open and understanding where the potential benefits are, where the best ties, and how we can best describe where we can have the impact when it comes to autonomy for vehicles in part of the program. But I think the critical thing is this is not single programs working together, but it's really a mission directorate level portfolio that just happens to be cast amongst several programs that we're a part of it too. And I think that's the most important thing. So with that, I'll pass it along to Doug.
Thanks, Jay, and thanks, Sanjay, for setting us up here. The Transformative Aeronautics Concepts Program, given that it's a seedling activity, will support all of the thrusts. So I want to just set the stage for what the program's about, and then focus in a little bit, like Jay did, on some opportunities in autonomy. The TAC, call it TAC for short, and I want to talk about some of the things in those green bubbles if you can read them. The program is designed, or the goal, it's designed to be set up for multidiscipline, interdisciplinary, cross-discipline, however you want to define that, activities. Not to say that there aren't activities that are single discipline as well, and I'm going to get to that. But the interdisciplinary, revolutionary, new concepts that also pull in the convergence from maybe non-traditional aeronautics, the things that we don't normally do, pull in from the rest of the world, and we want to pull that all together so that the barriers to getting to ultimately the goals, the objectives, the outcomes of the six thrusts that Bob talked about first. We want to knock down those barriers and challenge the aviation worlds, challenge the aviation systems status quo. So that makes this program fun, that an old guy like me can maybe become a little bit of a rebel. We'll look at that. But in the end, the program's set up to provide some flexibility so that both the NASA researchers as well as our partners and our collaborators then can explore and explore the feasibility of new ideas. the bottom of this slide, it mentions what the 3 projects are, and I want to just briefly mention those. The first one, the acronym is LEARN, or Leading Edge Aeronautics Research for NASA. We've had, and I would guess that many of you that are not NASA employees have heard of that, in that we've had a seedling activity, seedling fund, where we've supported or fostered new ideas both externally as well as internally. And this is, LEARN, we're going to continue the seedling activities externally. I'm going to talk a little bit more on my next slide about some of the specifics. Let me do this a little bit out of order. The last project listed there, Convergent Aeronautics Solutions, is kind of the corollary internally. This is our internal project, probably the newest concept for all of us in terms of organization, is to give the opportunity for our NASA researchers, to the ones that look to explore, entrepreneurially, some new ideas, and really in a rapid, quick turnover, take a look at feasibility so that the ideas can be incorporated, as Jay was just saying, in his program or elsewhere. The one that I have listed there in the middle, TTT, Transformative Tools and Technologies, or Transformational Tools and Technologies. Actually, there's a lot of papers being presented at this conference this morning. That project had a number of papers presented on the status of the revolutionary computational tools. And this is an area where maybe we're not so much multidisciplinary, but we're laser focused on specific, what's the leapfrog, what's the next step, what's the physics-based models that can just get us past a barrier that we, the community, have had in computations. So those are the three projects. The green little bubble over on the right just talks a little bit more about, again, soliciting new ideas. The scope of the program spans all of the 6 thrusts. So I'm going to talk a little bit more about autonomy, but the scope spans them all. The kind of work that the program invests in and performs, although perhaps it's a more focused, even a lower TRL or more of a feasibility determination, that doesn't mean that it's just on paper. It's hardcore analysis, real ground tests, and even flight tests, because flight tests, as Ed was talking, are not just a graduation exercise. They're part of the understanding and showing feasibility. So we plan to continue some of the seedling activities we've already done, continue the tools and also the technologies, the advanced materials or other technologies that TTT is doing across that whole spectrum, apply to all the thrusts. Okay, so how will we get into the kind of the autonomy world? Well, in every case, I look to kind of guide the research activities and consider what portfolio we invest in the new areas based on what I like to call, or what we like to call, big questions. Big questions in any one of the 6 thrusts, and particularly in autonomy. What we want to be able to do is ask the right questions. Otherwise, you'll never get the right answers. But those questions are based on the results of some of the studies that have already been talked about. John listed half a dozen or so outcomes from the NRC study, and similarly a bunch of things that came out of the NASA efforts. And hopefully, by asking those big questions, by performing the research to determine feasibility, even in this next year or year and a half, I'm hoping that we can provide some input then to the road mapping that's going on, and maybe redirect the planning once we learn some of these more wild and crazy new ideas. So ultimately, the goal of the program, it's a seedling program, so we're gonna grow these little seedlings into some real robust, I don't know if they're corn stalks or bean stalks or oak trees or whatever, that then would support the other programs or support the community. So let me talk about in each program or each project within the program some of the things we have going on. There is already research underway, like I said, in the external as well as some of the internal seedling. We've continued some of the legacy. Some of it's autonomy, a lot of it's not. There's a fair amount of what I might call intelligent systems or automation-like approaches. They can be used to help. In Learn, there's a number of activities that are currently going on. Some of them span from maybe what I might call integrated vehicle or integrated health management concepts. There's some new ATM tool or ATM concepts. All of those are, again, seedling activities. They could be brought forward. In the future, we'll look towards maybe taking more of a point of view of thinking of these big questions, more of a point of view of challenging the community, challenging you. We will fund activities that either literally are challenges or are more in that sense to bring the non-traditional partners in to converge with some of the more traditional activities we've got to solve these big questions, to solve many of those barriers or questions that came out of the other studies. In CAS, the primary goal there is to answer a feasibility question. I like to use the term wild and crazy idea. Well, maybe they're not that wild, maybe they're not that crazy, but if they can transform aviation, they can knock over some of the barriers. Well, is that idea feasible? So the focus is to answer the feasibility questions. If it's feasible, great. If it's not feasible, that's great too, because we will learn things. And in learning those, the plan is to merge those non-traditional disciplines as well. But in learning those lessons, that then can be brought forward into the other programs. And then finally, in T-Cubed, the work there is probably, well, it is the most focused on more singular disciplines, but that's because it's an important state-of-the-art computational tools, advanced technologies, whether they're in controls or materials. There's some specific things we've been focusing on, or even advanced measurements. All of those can help support autonomy. A couple other things I was going to mention. In our ongoing seedling activities between CAS and TTT, we've got a couple things going on. We've got some controls as an example. Some controls work that's called Learn to Fly, and that's not to teach new pilots, but think of the analogy of a fledgling bird. A fledgling gets pushed out of the nest, up there on the branch, and by the time it falls to the ground, it kind of, oh, I got a wing here, I got a tail, kind of flaps around and doesn't land, break its neck on the ground. It kind of learns to fly as it goes down. So by using things like, in a more engineering sense to that literal arm waving that I just did, real-time system identification, adaptive controls. I mean, it's not autonomy per se, but those kinds of tools then can be applied to a more autonomous world. So that's one thing we have going on in the program. Another thing that we have is we've been incubating several ideas in anticipation of this program getting off the ground. And within CAS, we've got several things going on. We're collaborating with Jay's program as well to learn what some of the issues are. And one of them is in the vertical lift area, looking at kind of what can we do? What is the next after that generation vertical lift vehicle? What does it look like? How do we pull in autonomy? How do we use a more electric propulsion system? How do we bring in some of the noise issues that rotary wing or other vertical lift vehicles often have? So we've been looking at incubating some ideas there. We've got a team working that right now. There's several others. I'm not going to get into them in depth. Most of what I have going on in the program now is not autonomy. But as we move forward, we ask the big questions of you. You ask questions of us, and we'll get into new ideas, new concepts that will support the autonomy, the assured autonomy thrust.
Wonderful.
thank you.
Thank you, Doc. Thank you, everybody, for your overview of NASA's programs and where we are currently with respect to autonomy thrust planning. Appreciate it. We have time for questions, discussion. Any thoughts you have, any questions you have, I would welcome that. Yes, please. What happened to reducing carbon footprint and noise at NASA goals?
Yes, well, Bob, why don't you?
But they're part of our strategy. They're a major central part of our strategy. Can I pull up if you put my charts back up, I can show. We have, autonomy is just a single thrust among 6. And so those elements, low carbon, efficiency, low noise, are part of the other 5 thrusts.
Oh, this panel is only
specifically.
focused on the autonomy thrust. There are 6 thrusts. So those other things are also part of the NASA's program.
Yeah, and I was about to say that's probably the largest part of our
Yeah,
portfolio right now is on things like the improved
know if they'll link
environmental
back up from there or
performance,
not,
the
but-
improving the efficiency of aircraft. So that's definitely a long, a significant part of the portfolio today. Very focused on what we call the thrust area 3, the ultra-efficient commercial vehicles, and the transition to low-carbon propulsion.
Yeah, I alluded to ERA, and 2 of their, they have a goal relative to fuel burn, which directly relates to carbon and noise and then emissions.
And you can see the thrusts are up there now.
So those 6 thrusts. Yes, sir.
So I'll make a comment or two. Certainly, from the context of the UTM exercise that I mentioned briefly, the connection with a variety of automotive manufacturers that are driving autonomous vehicles, Google, not an automotive manufacturer, though maybe, there's very close coupling with them. The ITS, Intelligent Transportation System associated with DOT and those efforts going forward are all parts of things that we are looking to leverage and learning. We've got a variety through the centers, I should say, agreements to share information on things in terms of the autonomous car relative to what the community refers to as localization, that they are addressing. They can manage their travel with an autonomous vehicle just fine on highways and local streets as long as a policeman isn't out there holding traffic, or a soccer ball runs across, or a mom in a baby carriage. They need to be able to localize themselves in their environment and identify other actors in the path of that particular trajectory, if you will. We've got similar sorts of issues, and that technology at that level of identification of pieces is precisely what we're trying to bring in. So yes, closely coupled, and there's a lot of work going forward in there that we want to take advantage of. Ed, did you have?
Yeah, I mean, just picking up on that theme, I mentioned about testing a due regard radar. Now that's something that one would not need necessarily with a manned aircraft, but when you start talking about self-separation, then that's exactly the same sort of thing that you see in an automobile, and is based on those kinds of concepts. It's a much more powerful radar and more accurate radar, but it's the same sort of thing that you see within a car, that you're either have somebody in a blind spot that you're following too closely, and that it could take over the control of your automobile and can stop for you.
Other questions? Yes, Raman, please. The question is about how much funding would be for autonomy and what is the time period when funding will start. What will be the mechanism for that?
Well, I'll start. I was looking at John, John's looking at me, so I guess I'll start.
I'll chip in. Good.
Well, I think at a top level, one of the points we try to make here is that the opportunities will be across the program, so there's not a single, a funding mechanism that will be used to support autonomy. It'll be, integrated into each of the programs. Some of that, as I think Ed described in detail, is already ongoing. So UAS and the NASA is about a $30 million a year initiative. John has, for example, the UTM initiative that's just getting off the ground, has some funding definition to it in a set of partnerships and an RFI that went out that generated, I don't know, 100 or more, or over 100 responses. Yep. So and we plan to grow this area over time, as we transition. So, like I said, Ed's got about 30 million, I think, in AOSP. It's probably on the order or more.
It's about that. I'd say so is roughly a $30 million activity. We're leveraging elements in the Smart NAS project. Mm-hmm. Not entirely. That's a $40 million effort. Giving you ballpark figures. So from AOSP, there's a substantial bit of contribution to this. But again, we have much to define in terms of the way we're going to be leveraging and building that. Hopefully, there'll be opportunity for growth going forward, but we have to deliver on what we've got right now. So those are the rough numbers.
And I think just skipping Jay for a minute and going to Doug, I mean, that's going to be an annual opportunity to bring up new concepts and new ideas and those.
Right, specifically in the Learn project, which is a totally external kind of challenge, as well as topics, if you will, that are put out in the NASA research solicitations. It is annual or semi-annual as we develop that. That has been going on for a couple years.
And that total is about 10 million a year.
About 10, yeah.
And that encompasses the entire, set of questions that might be asked.
Right.
Yeah.
Right, and from our perspective, it's a little bit different, and I'm certainly not going to comment and try to project or predict what future budgets might look like, but I will say at least of how we're looking at the problem right now is I think autonomy will be something that's incorporated within the existing projects that we have now in some of the technical challenges, and I'm not saying that things might not change in the future, but at least of what's in our current or more near-term planning, I think it will be incorporated in that rather than a standalone autonomy type project within the Advanced Air Vehicle program is more likely. But getting back to the mechanisms, I think we'll still continue to rely on the traditional ones that we've had, various kind of agreements that we do with some of our other partners, whether they're in industry, other government organizations, or if through the NASA research announcement, for example, if we have specific topics that we want to solicit funding, it would be part of, I think, the traditional type of NRA process that we use, though.
But watch this space. It'll become clear as the roadmap starts to become developed and as the programs adopt key elements of that roadmap for funding. Hopefully that your question will become much more clear as to the resource availability, the mechanisms, and the time frames for submitting ideas and so forth.
So John and Bob, a related question. I know that NASA is kind of developing the roadmap currently internally. So two questions. Part of that is, what is your timeline for having a good draft of the roadmap? And what would be the process after that timeline to seek feedback from the broader community?
So the timeline is 2015.
By the end
Fiscal
of
year
2015.
15. Yeah, certainly expect to have it done before that. But still, that's the timeline for commitment around that draft roadmap. We certainly we are building that roadmap not only based on our program and our centers, contributions to this. We're basing it on the NRC report, which was a public solicited opportunity. So we feel that we can work within some good external guidance and internal expertise to build that. And after we do our own internal due diligence around that plan, we're looking to get additional feedback on it. And as mentioned by all of us in terms of whether you call it lead, follow, watch, or just elements of partnership around execution of that, the opportunity is going to be strong and even nearer term to reach out to elements of the community to suggest that we have something we can work together and get their additional feedback and insight on how we structure particular parts of that. So think later this year, but I'll hesitate to give you an actual date. We're working as hard as we can on that.
Okay, wonderful, thank you.
Good one.
Questions? Yes, over there. What is the connectivity to the space technology program?
Yeah, that's correct. And as part of the ICAS process, we did talk not just to the aeronautics centers, but also to some of the space centers, and we talked to the space technology mission director and so forth. And I think, so there are definitely areas that where there are common problems. I mean, the kinds of things that were brought up through the NRC study, there are equivalents on the space side, so that there are opportunities. I'd say, similar to where we are with the roadmap, they're sort of nascent right now. We think we know where to go within the center, within within NASA to start to explore and develop those opportunities. So the plan is to do that, so we can leverage and they can leverage, and hopefully we can get more done with the resources we have.
And not addressing space technology mission director specifically, but in the work that we have done to this date of trying to help us understand what an autonomous architecture for airspace ops could be, we reached out and actually getting continued support from colleagues at JPL, certainly from the remote planet and the science mission around the unmanned spacecraft. They have a tremendous amount of autonomy capability that we are leveraging and bringing in regarding our ability to build that right architecture up front. So we understand there's certainly a lot more than just ARMD insights into this, and we're doing our best to find that and be inclusive for our own benefit.
Other questions? Yes.
The answer is that it's not enough for the machine to be autonomous. We have to make sure it's both safe and secure. And so assured is a general, sort of a generalized term for capturing the safety and security issues, and really putting the emphasis there that one of the things that NASA and ARMD can bring to the table is making sure the research is done so that when autonomy is applied, it is done in an assured safety and a security assured, and mostly safety. We don't work as many as the security aspects, but they are synergistic. So make sure that those are applied in an assured way.
So another question that I have for the panel is, DoD has invested a lot in autonomous aircraft. I mean, there was the KC-KX, I believe, helicopter doing autonomous operations in Afghanistan, cargo delivery. Then DARPA has done a lot of effort in autonomous UAV refueling. So how is NASA leveraging the DoD efforts and coordinating? How do we, to make sure we don't duplicate, how do we leverage what they have done?
I'll provide one example. We have others, I'm sure. On the chart that I had up where I had the airspace classes and showing opportunities for different autonomous applications. There's one regarding reduced crew operations. We have a very strong partner with the Air Force right now, Air Mobility Command, around the system opportunities to enable. Some people think of it as single pilot. I don't want to call it single pilot. It's a little bit too restrictive in terms of the way we want to be applying this. But ways in which advanced communication networked architectures can, as well as on flight deck avionics in commensurate with the system, can allow for reduced need for crew based on autonomous capability that can help with decision making, to help with off nominals and other elements of a flight path that requires that advanced capability and decision support. So there's one area of interest, again, that's in their C-17s and their commercial transports, but they see quite a bit of opportunity to find value in that. So.
Yeah, a couple of forums that we've been involved in now. What we're doing with UAS and the NAS is leveraging those technologies for civil applications. And so the Sense and Avoid Science and Research Panel, we're represented at the executive level as well as the working group level on all of that, so we have insight into the work that's going on in all the branches, as well as the UAS Aviation Rulemaking Committee, which there are DoD representation on that. And so that's bringing to the table and allowing us insight into specific work that's going on, not just in autonomy, but autonomy as well as other technologies as well. So I would say that we really have a seat at the table at all of the major forums where this type of work is going on. And so I see that continuing into the future.
Yeah, and I'll comment too is, I mean, it's certainly not limited to autonomy. If anything, autonomy is probably one of the smaller areas where we have some of those collaborations, but there's just been a tremendous opportunity to collaborate with the DoD on various things, you know, anything from engine development to helicopters to fixed wing, so on and so forth. And so we've got, I think, a lot of those connections that are already in place, you know, as Ed mentioned, you know, some specific to the UAS, but even to these other things, we've got, at least at our level, to our peers, you know, within those other organizations, a good type of connection. And I think some of the efforts that we see also going on within the DoD are also helping with that communication. They're able to articulate their plans through that community of interest and the road mapping efforts that they're doing. We have insight into that helps with that type of collaboration at the higher level. And then you have very, I think, strong interworking relationship, you know, between the center and the various research labs and things like this. So, you know, you alluded to the work of the autonomous vertical lift. You know, so we've got a lot of insight into what the Navy and what the Army are working on in those areas, and that also helps influence what is it that we should do, because we don't need to repeat what they're necessarily doing, but it perhaps helps us carve out where's the civil application and where can we get the focus that we really need to have.
Wonderful. Thank you. Over there.
So, yes, I mean, there are a variety of opportunities that we're exploring. We have no agreements in place right now that are leveraging any of that, but I mean, you can look at any partner, any international partner, and see interest and capability in UAS. The largest share of that is on the vehicle side itself, not the operational environment. So from my program's perspective, particularly interested in reaching out to those nations that have that, that advanced capability on the vehicle side that could find value in the operational capability that we bring from, whether it be UTM or other elements of autonomous elements. So I just had a recent connection with folks at Canada, NRCC, that are expressing particular interest in just the vein you're talking about. But nothing in place now, but I see much opportunity. We're certainly open to it to the greatest degree that we can sponsor that.
I would just, I guess, add that philosophically, you know, to the extent that, you know, we're advancing issues like safety, where we can support the coordination on standards so that, you know, things can interoperate and we can help harmonize, you know, operations and standards and procedures and so forth. I think that's where we can certainly add value. I think we'll probably be selective in you know, in using that kind of philosophy to decide where we're going to partner and where we may decide that we're going to use a U.S. partnership to perhaps push a technology, for our own purposes. But I think there are definitely areas using that philosophy where we're getting together as a globe makes a lot of sense.
Yeah, and one comment I would make on that too is right now, I mean, when you look at the potential list of partners, even within the United States, that's a long list as far as what is it we're going to do, who we would work with, and things like that. So we certainly haven't gotten to the point where we've exhausted where we can look at and we've got to partner with a particular organization in another country because that's the only way to get the work. So right now, especially in that early phase, that's certainly influencing a lot that we do. But the other thing I'll just comment on very briefly is when we get into autonomy, especially maybe to some specific applications or on the vehicle side, this is the area too where we also have to start being concerned about export control regulations and things like that oftentimes we don't think about, but it's a very important aspect that we've got to think about when we are setting up those kind of partnerships, and it does sometimes limit what we can and who we can work with on certain things, by definition.
And so for the UAS and the NAS project, we're working with operations from an ICAO perspective, from COM with the international forums there. And so it's something that, as Bob mentioned, is selective. I mean, I don't know that we necessarily need to partner with folks where it's the Wild West out there for UAS, but that have a parallel interest in safety and interoperability between manned and unmanned aircraft. Then certainly we're looking to them to understand the experiences, sharing data, things like that for interoperability. And again, for our UAS and the NAS project, we have a seat at the table at those international forums.
And from my perspective on operations, so much of what we do, I don't want to say it's pre-competitive, but it certainly has the broad benefit, in fact, benefit to U.S. participants in the system, to have a safe system, to have an efficiently functioning system. So we've been aggressive in reaching out internationally to bring in partners to do that, but we are somewhat unique in terms of our ability to engage, where Jay's point about the competitiveness issues are very real on the vehicle side, and we have other opportunities on the ops side that we leverage as well as we can.
Wonderful. Sorry, we are running out of time. We are scheduled till 4 o'clock, and this was being live webcast, so I will have to end this, but I don't know whether you are available for a few minutes for people to ask questions officially. So we will end the official panel. Unofficially, what?
No, we're fine. Yes.
Yeah, you're flying autonomous aircraft back?
Yes, we are. Yeah.
All right. Are there any pilots in here, serious commercial pilots in here? No?
No.
Oh.
You got his hand right there.
You're a pilot? Okay. So I just wanted to, I'm very excited right now that NASA is looking into autonomy research for civil aviation. Back in 2005-06, I had written a white paper and sent it over to NASA ARMD headquarters, say, hey, it'll be a great thing for NASA to get into autonomous civil aircraft research, and I didn't hear anything. So I ran into one of the leaders and I asked him, why aren't you doing anything about it? He said, your ideas are great, but the Pilots Association in Washington, D.C. wouldn't let us go forward with it. So, I don't want to denigrate anybody, but what I'm saying is I'm so excited that we have gotten past that hurdle, and NASA is very much, made it a very visible part of their programs and is moving forward. So very exciting times, and I want to thank all the panel members for taking their time and the audience for your insightful questions. So big hand to the panel members, please. Thank you very much.